Go.
Go ahead.
Go.
Now.
Go.
Go.
Now.
Hi, today we will be talking about energy. Our first topic in the unit of energy is work. Work equals force, which is measured in newtons, times displacement, which is measured in meters. The unit of work is joules. For example, if we have a problem where the force equals 5 newtons times the displacement, which equals 3 meters, we will work it out and get 15, not newtons, not meters, but joules.
Go, you're good.
Hey, I'm Chet Hoffman. The next topic in our unit of energy is power. Power is the rate at which work is done. As we learned in the last unit, work is measured in joules, and power is just joules over seconds. It's measured in watts. For example, if we had 15 joules in 5 seconds, that would be 3 watts of power.
You're Gucci.
Our next topic of energy is kinetic energy. Kinetic energy is the energy acting on an object that is in motion. The equation for kinetic energy is 1/2 mass times velocity squared, and it's measured in joules. As you can see right here for our example, if we have a mass of 20 kilograms and a velocity of 4 meters per second, you do 1/2 the 20 kilograms times the 4, which is velocity squared, and you get a kinetic energy of 160 joules.
Potential energy is the energy acting upon an object when it has height. Therefore, the equation is gravity times height times mass, or gym. So, in our example, we drew a roller coaster. When the roller coaster, which has a mass of 25 kilograms, is at a height of 50 meters, gravity is obviously 10 meters per second squared, the potential energy will be 10, gravity, times 50, height, times 25, the mass. And it gives you a potential energy of 12,500 joules.
Good. Anthony, go ahead.
Alright, our next point will be law of conservation of energy, which basically says that the energy you have in the beginning, the initial energy, will be the same as the energy you end up with, your final energy. So basically, your potential energy in the beginning, initial, plus kinetic energy in the initial is equal to your potential energy final plus your kinetic energy final. So we explain this through the roller coaster. When you're at the top of the roller coaster, you have zero joules of kinetic energy and 1,000 of potential energy for this example. And at the end, when you have potential energy 0 and kinetic energy 1,000, these numbers correlate because of this law, so when we plug in these numbers, 1,000 joules plus 0 joules equals 0 joules plus 1,000 joules. EI equals EF.
So class, another really chill way to think about work is through the work kinetic energy theorem. The work kinetic energy theorem states that work is equal to the change in kinetic energy. So, for example, with the roller coaster, at the top the kinetic energy with the roller coaster is 0, and at the bottom the kinetic energy is 1,000. So there's a change of 1,000 joules of kinetic energy. Therefore, the work done is 1,000 joules. Say, Jack, the sun puts out twice as much solar energy in 2 hours as it does in 1 hour, but the solar power of the sun is the same from 1 hour to the next. Distinguish between the two terms, solar energy and solar power.
Well, Dan, solar energy is merely energy from the sun. Solar power, though, like power in general, is the rate at which energy is transferred. Solar power is therefore the same from hour to hour, whereas the amount of solar energy depends on the amount of time energy is transferred.
Go!
Say, Jack Penn, when a rifle with a longer barrel is fired, the force of expanding gases acts on the bullet for a longer distance. What effect does this have on the velocity of this emerging bullet?
Well, Dan, when a rifle with a long barrel is fired, more work is done as the bullet is pushed through the longer distance. A greater kinetic energy is the result of the greater work. So, of course, the bullet emerges with a greater velocity.
On, go!
Potential questions. Why is it easier to stop a truck with a lower mass going at the same speed as a truck with a higher mass?
Stopping a lightly loaded truck of the same speed is easier because it has less kinetic energy and will therefore require less work.
2, 1, go!
Say, Jack, if your friend pushes a lawnmower 4 times as far as you do while exerting only half the force, which one of you does more work, and how much more?
Well, Dan, your friend does more work.
Good to know.
4 times 1/2 is greater than 1 times 1. So therefore, the friend does twice the work.
On you go.
Hey Jack, which requires more work? Stretching a strong spring a certain distance or stretching a weak spring the same distance?
Well, Dan, stretching a strong spring will require more work because to pull the strong string, you will need a greater amount of force.